Okay then, so let's um, complete this discussion of the sort of fundamentals of topos logic. I mean, it's really a sort of introduction to them, but anyway, um, first thing I want to do. So we've been looking at this there exists condition, and in the last video, I showed with a rather lengthy proof involving the kind of image factorization Goldblatt definition of there exists quantifier, existential quantifier, that insets this Kirby-Joyle condition for a C satisfying this there exists quality like this, sort of simplifies. So what I want to start with is a much cleaner proof to that, a different proof, because it's nice to see things from different perspectives. And so basically, in this sort of original language, the general statement for a general topos is that C is in the extension of there exists Y and B such that theta, if and only if there exists an epimorphism S from some zeta to T. I mean, here C here is an arrow from T to C, from T to A. So the general condition is there exists an epimorphism S from zeta to T, and there exists an arrow R from zeta to B, such that CS comma R is in this extension of theta over the x's and y's. And here we can think of theta as an arrow from A times B to omega. Okay, so that's a general statement, but I showed last time that this simplifies in the sense that, I mean, in set, if this works, as in if C is in this sort of existential extension, then in sets, the only epimorphism we need to use is the identity. So we can just set zeta equals T and use an identity there. So I've got another proof to this. So the claim then is that in set, we have that C is in the extension of there exists Y and B such that theta, if and only if there exists an arrow rho from T to B such that C comma rho is in the extension of theta over the x's and y's. Yeah, let's go. Let's prove this. So it's quite straightforward, actually. It's quite a short proof. So this is the sort of situation in general. Now, of course, if we can pick S is equal to the identity of T, and we can get that CS comma R is in this extension of theta over the x's and y's, then according to that Kirby-Joyle condition, we have that C is in the extension of there exists Y such that theta. So clearly, this condition here, this kind of condition is sufficient. But is it necessary? Well, it's necessary in sets. Okay, so let's show that. So what we're going to do, we're going to suppose that the general the kind of general Kerpisch-Oyl condition holds that there exists a sort of general epimorphism, and then we're going to prove that actually using the identity will do. So suppose we have an arrow C from T to A, and there exists an epimorphism S from zeta to T, and there exists an arrow R from zeta to B, such that CS, R is in the extension of well, I mean, I suppose what we could actually start with, we could suppose that C is in the extension of there exists Y and B such that theta, and then according to the Kerpisch-Oyl condition, we get that there exists an epimorphism S from some zeta to T and an arrow R from zeta to B such that CS, R is in the extension of theta. Okay, now, I mean, this is sort of the situation, and the strategy here, I mean, we have this zeta with this S and R such that CSR is in this extension and the thing is, because we're working in the category of sets, we'll assume that the axiom of choice holds. So we have that this epimorphism here is a split epimorphism, so it has a section I, and then the idea is we basically use that. So we define rho is equal to R after I, and it just works. Okay, so we have a section I of S, so that's an arrow from T to zeta such that SI is the identity of T. So we define rho is equal to R after I, like so. So since we have that CS, R is in the extension of theta, we have that there exists a K such that CS, R is equal to this extension after K. So multiplying on the right by I, we have CS, R after I is equal to the extension over theta after K after I. And the left-hand side is equal to C, Ri, which is C, rho. So we have that C, rho is in the extension of theta over the x's and y's, and that's it. So it's a very nice short proof in this case. Okay. Right, so the next thing is to understand this for all this exist condition better. So there's this way of defining exists using what I call the double for all formula, which is how McClarty originally defines it. And I'm not sure how useful it is, but I think it's sort of an interesting exercise to try and unpack that formula. Although, to be honest, doing so doesn't seem to lead to something which is especially applicable. But who knows? Maybe it'll be applicable in some cases, and it's certainly sort of interesting to look at it in a different way. So, basically, to unpack that double for all formula, which I'll explain what it is in a minute, but to unpack it, we're going to use two results which we've sort of come across in this little series of 5 videos. So the first one is that for C from T to A, we're going to have that C is in the extension of phi implies psi if and only if C to the minus 1 of the extension of phi is contained in C to the minus 1 of the extension of psi. And that happens if and only if for every arrow S from zeta to t, we have that CS is in phi implies CS is in psi. So that's simply the Kirby-Joyle equivalent condition for this. Also, I think, I'll have to check this, but I think when C is monic, we can sort of further simplify this condition to become that C intersection extension over phi is contained in extension over psi. And I think you can probably even take out this C intersection from the outside and put a and classifying arrow in the inside of this extension and get an equivalent expression. So there's that sort of what's one of the tools we use. The other tool we use, so I think this is this last bit is corresponding to theorem 13.6, I think. The second tool we use is C is in the extension of for all y theta if and only if C times 1b is in the extension of theta over these x's and y's. Okay, so let's use these then to simplify things. So this is our it's what I call the for all definition of the existential quantifier, at least as a term, as a formula. So we define there exists B in B such that theta as for all W in omega, we have that for all B in B, we have that theta implies W, or that implies W. Okay, so suppose we have theta as an arrow from A times B to omega. Suppose we have T as an arrow from T to A. Now, C is an arrow from T to A. Now, C satisfies this. There exists a B such that theta, if and only if C is in this extension over A for all W, for all B, theta implies W, implies W. Now we use this result here to express that as equivalently C times 1 omega is in the extension over the A's and W's of for all B, theta implies W, implies W. Now we use number 1 to rewrite that. Say it's equivalent to saying for every arrow st comma s omega from zeta to t times omega, we have that C times 1 omega after st, s omega, which is just cst, s omega. We have that's in the extension of for all b theta implies w, implies that it's in the extension of w. So what's this last bit mean? Well, here's a general kind of way of simplifying it. So we have, in general, say we have some arrow from star, where star's in the object, some arrow a double dash, w double dash. Well, we have that's in the extension of w over these a's and w's, if and only if p2 after a double dash, w double dash equals true. Okay. So that's how we can simplify this thing that it implies. Now, what about the first bit? When does this go in this? Well, in general, I mean, it's a similar kind of methodology to work this out. So I'll just scan through it. You can pause the video or whatever. So basically, for an arrow a dash, w dash from some q to t times omega, we're going to have that a dash, w dash satisfies for all b theta implies w if and only if for all gamma q, gamma b from some object gamma to q times b, we have the a dash after gamma q, gamma b is in extension of theta over the a's and b's, implies w dash after gamma q is true after exclamation mark gamma. So the punchline then, so we have this sort of simplified condition for that. Well, simplified in inverted commas. So the punchline then is C satisfies there exists a B such that theta, if and only if C is in if and only if for every arrow st, s omega from some zeta to t times omega, we have that cst, s omega satisfies for all b theta implies w implies s omega equals t after exclamation mark zeta. And we have a kind of simplified, a explained kind of description of when this first part happens, basically with this text in purple. Okay. Now, this simplifies a little bit when C is monic, because when C is monic, C times 1 omega is monic. And we're going to have that C is in this extension of there exists B such that theta, if and only if C times 1 omega intersection extension of for all B theta implies W is contained in the extension of W. Okay. Now, the other thing I wanted to talk about is something which I'm not 100% sure about because I've just started learning about this. But this is from Johnston, and it's basically a way of thinking about these kind of universal quantifiers in terms of adjoints and those interesting functors f star, sigma f, pi f, which were going between the slice categories. So I'll just extract what I think is the most pertinent point from this for this discussion for a start, and that is that, well, I mean, this is the basic sort of conclusion that I think is the case, although, as I say, this is all quite new to me, is that we can have a very direct way of describing this sort of extension over this existential thing. So the extension of there exists a B such that theta over the A's is simply the image of P1 after the extension of theta over the A's and B's. So here, again, theta we can think of as an arrow from A times B to omega. And there's an interesting kind of implication of this, and that is in particular that that means that we can write P1 after this extension over theta as an epimorphism followed by this image arrow, this monic. So this image arrow is equal to the extension of there exists B such that theta. So what we have is like, to say this again, we have that P1 after the extension of theta over the A's and B's, so that's this stuff, is equal to this image thing, which is equal to this left-hand side. So that's extension of there exists B such that theta after some epimorphism, because this diagram is basically just showing an epimonofactorization of P1 after the extension of theta. Now that's interesting because I think this is exactly what we wanted when we were discussing yet another way of looking at this existential quantifier. And that was I think this was in the last video. I just briefly mentioned it. That was here. Okay. So if you remember, like the general definition, I'll just go through it again. From an arrow C from T to A, we have that C is in this extension over the A's of there exists a B such that theta if there exists epimorphism S from zeta to T and there exists an arrow R from zeta to B such that CS comma R is in this full extension. Okay, so what I wanted to do I mean, I kind of didn't like this I mean, I had a problem with this, which is like, do I really have to check all of these epimorphisms? Like, how do I find this epimorphism S that makes this work when I know that C satisfies this? How do I find the epimorphism? And the answer, I think, is this diagram, or I guess it's this diagram. So the idea here is that, say we know that C does belong to this existential extension, then we want to actually find this S and R. And so I think we can do it now, because look at this square. This square is the start of this construction. And I was confused about this at the time because I was thinking, well, how can we find an epic? The idea is we want this kind of commuting square. But this commuting square is precisely, I think, what we want, because we now know that this is just the image of, or at least we guess that this is the image of P1 after the extension. Okay, I'm using X's and Y's instead of A's and B's respectively, but it's the extension, it's the image of P1 after the extension over X's and Y's of theta. Okay, so I mean, all the bottom left part of this square is just the epimonofactorization of the top right part of this. The bottom left part of this square is just the epimonofactorization of the top right part of this square. So of course we have this commuting square. And now given this, and given that C belongs to this extension of there exists Y and B such that theta, well, that means there exists a H such that C is equal to extension over there exists Y such that theta after H. If we pull back this epimorphism I along H, then we get H to the minus 1I, and I believe we can set that to be S. The other kind of arrow in this pullback square we'll call V, and then I guess if we do P2 after the extension of theta over the X and Y's after V, we can call that R, and then we have CS comma R is in this extension of theta over the X's and Y's. Here, I might as well say that A equals X and B equals Y, because I've been using kind of two types of notation at the same time. Now, I'll just say something quickly, because this theory from Johnston is much deeper than, I only really do the tip of the iceberg at the moment, but basically for an object X in a topos E, We let P of X denote the full subcategory of the slice category of E over X, restricted to the objects of E/S corresponding to monics in E. Remember that for F, we have this logical functor. So suppose F is an arrow from X to Y. So we have this logical functor from the slice category of E over Y to the slice category of E over X called F star. I think this is called the pullback functor. So if we restrict this to monos, it gives us this functor, which we can call f to the minus 1, which is a functor from this. I mean, this is really the kind of lattice showing which parts of y are containing which parts. And anyway, this is a functor from p of y to p of x. And then there exists f is the left adjoint to f to the minus 1. And that's basically the functor which I used in the construction. So, I mean, in this case, we had that f is an arrow from a times b to a, and here to get im, the image of P1 after the extension of theta over the A's and B's, all I'm doing is operating this functor that exists f that I just described on this monic, the extension of theta over the A's and B's. And there's various other things. The for all quantifier also appears as an adjoint going between slice functors and associated with these functors between slice functors, and it's really a very nice theory.